Hello everyone, welcome to VYSH IAS YouTube channel. This is continuation of SHANKAR IAS Environment series. You can watch the chapters which are covered in the playlist available in the channel. Also have a look at all other playlists which are designed for UPSC. These are all part of paid courses, but if response is good, they can be put here for free. So subscribe and leave a feedback comment. Serious aspirants can contact Vice Sir on WhatsApp 7200681675 anytime for test series details or foundational videos. This is Chapter 19, Ozone Depletion. Ozone is a natural gas. It is an allotrope of oxygen. Allotrope is something which exists in different physical forms. It consists of three atoms of oxygen bound together in a non-linear fashion. Chemical symbol of ozone is O3. It is found in two different layers of the atmosphere. Ozone in the troposphere is bad because it contaminates the air. It helps to form smog, which is not good to breathe. Ozone in the stratosphere is good because it protects life by absorbing ultraviolet rays from the sun. Ozone layer is very important because it efficiently absorbs ultraviolet light, thus acting like a sunscreen. UV rays cause direct damage to the genetic material or DNA of animal and plant cells. Exposure of mammals to UV light has been shown to act on the immune system, making body more susceptible to diseases. Ozone protects oxygen at lower altitudes and also from most of the ultraviolet radiation from reaching the Earth's surface. It helps in reducing the risks of mutation and harm to plant and animal life. Too much UV rays cause skin cancer. It is also harmful to plants and animals. And life on Earth could not exist without this ozone layer because it acts as a protective shield. Hoolock gibbon is the only ape found in India. Rest are all macaques and langurs. In India, it is distributed in the northeast India. Palms are typically unbranched trees with only one trunk called the cortex. Ozone depletion, change in equilibrium. The equilibrium between the formation and destruction of ozone has been upset due to the influx of several substances into the atmosphere that will react with ozone and destroy it. The rate at which ozone is being destroyed is much faster than the rate at which it is being formed. It implies that there is a significant decrease in the concentration of ozone in a particular region of the atmosphere, hence the name ozone depletion. Example is the atmosphere over the Antarctic, which has only very few percent of the ozone that has originally occurred there. Actual realization of ozone depletion came only in 1985. Sources of ozone depletion: chlorofluorocarbons, CFCs. These molecules are made up of chlorine, fluorine and carbon. Where it is used, they are used as refrigerants, propellants in aerosol sprays, foaming agents in plastic manufacturing, fire extinguishing agents, solvents for cleaning electronic and metallic components, or freezing foods, etc. Two-thirds of CFC is used as refrigerants, while one-third is used as blowing agents in foam insulation products. Why CFCs are used even though it is considered dangerous to the environment? It has a wide and varied application due to its properties like non-corrosiveness, non-inflammability, low toxicity and chemical stability, etc. Lifetime and removal of CFCs. CFCs cannot be eliminated from the atmosphere by the usual scavenging process like photodissociation, rainout and oxidation. The residence time of CFCs in the atmosphere is estimated to be between 40 and 150 years. During this time, CFCs move upwards from the troposphere to the stratosphere by diffusion. The escape of CFCs. CFCs enter into the atmosphere by gradual evaporation from their source. Since CFCs are thermally stable, they can survive in the troposphere, but in the stratosphere they are exposed to UV radiation. They escape into the atmosphere from a discarded refrigerator and from other sources. Chemical reaction. The molecules of CFCs, when exposed to UV radiation, break up, thus freeing chlorine atoms. A free chlorine atom reacts with an ozone molecule to form chlorine monoxide. Molecules of chlorine monoxide further combine with an atom of oxygen, resulting in the formation of an oxygen molecule and reformation of the free chlorine atom. And the depletion of ozone is catalytic. The element that destroys O3, that is ozone, chlorine is being reformed at the end of the cycle. Here, chlorine is reformed at the end of the cycle. A single chlorine atom destroys thousands of ozone molecules before it encounters reactive compounds like nitrogen or hydrogen that eventually return chlorine to its reservoirs. Here you can see ultraviolet light causes a chlorine atom to break away from the CFC molecule. This free chlorine atom hits ozone molecule. The chlorine atom pulls one oxygen atom away. And on the other hand, a free oxygen atom hits the chlorine monoxide molecule. The result is another free chlorine atom is forming and the other one forming oxygen molecule. And this free chlorine will continue to deplete ozone in the same way. A fact, barking deer or common muntjac is the mammal with the lowest recorded chromosome number. It gives calls similar to barking, usually on sensing a predator. Status least threatened. CFC substitutes or characteristics. The substitute for CFCs should be safe, low cost, increased energy efficiency, effective refrigerants with low ozone layer depletion potential and low global warming potential. CFC-12 is a widely used refrigerant. HFC 134A is the most promising alternative, and these can also be used. Nitrogen oxide. Source of nitrogen oxide are mainly explosions of thermonuclear weapons, industrial emissions, and agricultural fertilizers. Chemical reaction. Nitric oxide catalytically destroys ozone. Nitric oxide combines with ozone to give nitrogen dioxide and oxygen. Nitrogen dioxide combines with monoxide to give nitric oxide and oxygen. Escape of nitrous oxide. Nitrous oxide is released from solid through nitrification of nitrates under anaerobic conditions, nitrification of ammonia under aerobic conditions. It can gradually reach the middle of the stratosphere. It is photolytically destroyed to yield nitric oxide, which destroys ozone. Other substances, bromine containing compounds called halogens and HPFCs, that is hydrobromofluorocarbons, both used in fire extinguishers, and methyl bromide. Methyl bromide is a pesticide. Each bromine atom destroys 100 times of more ozone molecules than what a chlorine atom does. Bromine combines with ozone, forming bromine monoxide and oxygen. The bromine monoxide further reacts with chlorine monoxide to give oxygen and free atoms of bromine and chlorine. These free atoms, chlorine and bromine free atoms, can further react with ozone. Sulfuric acid particles. These particles free chlorine from molecular reservoirs and convert reactive nitrogen into inert forms, thus preventing the formation of chlorine reservoirs. Carbon tetrachloride is a cheap and highly toxic solvent, and methyl chloroform. It is used as a cleaning solvent, propellant, etc. and other aerosols are also responsible for ozone depletion. Monitoring the ozone layer. Few organizations help in monitoring the atmosphere. They form a network to communicate about the atmosphere, including ozone layer monitoring. Few of them are World Meteorological Organization, World Weather Watch, Integrated Global Ocean Services System, Global Climate Observing System. Role of polar stratospheric clouds in ozone depletion. There are three types of stratospheric clouds. They are nacreous clouds, which extend from 10 to 100 km in length and several kilometers in thickness. They are also called mother of pearl clouds as they glow with a seashell-like iridescence. Iridescence is they change color as the angle of view or illumination changes. The second type of clouds contain nitric acid instead of pure water. Third type of clouds have the same chemical composition as nacreous clouds but form at a slower rate, which results in a larger cloud with no iridescence. That is, they do not change color or they do not appear to change color. The chlorine released by the breakdown of CFCs exists initially as pure chlorine or as chlorine monoxide, either as chlorine or as chlorine monoxide. Chlorine monoxide is active chlorine or unstable chlorine. These two forms further react to form compounds like hydrochloric acid and chlorine nitrate, which are stable, that is inactive chlorine. Hence, they are reservoirs of chlorine. Chlorine combines with methane to give HCl and methylene cation. Chlorine monoxide combines with nitrogen dioxide to give chlorine nitrate. The stable compounds HCl and chlorine nitrate are reservoirs of chlorine, and therefore for chlorine to take part in reactions, it has to be freed from these compounds. There is a correlation existing between the cycle of ozone depletion and the presence of polar stratospheric clouds. That is, the ice particles of the cloud provide substrates for chemical reactions which free chlorine from its reservoirs. Usually the reaction between HCl and this chlorine nitrate is very slow, but this reaction occurs at a faster rate in the presence of a suitable substrate, which is provided by the stratospheric clouds at the poles. HCl plus chlorine nitrate. HCl when combined with chlorine nitrate give molecular chlorine. It results in the formation of molecular chlorine and nitric acid. Here is the equation. Molecular chlorine formed in this reaction can be broken down into atomic chlorine and ozone depletion reaction would continue. This picture would be helpful in understanding the reaction. The molecular chlorine formed in the above reaction can be broken down to atomic chlorine, and this ozone depletion would continue. PS says that is the clouds not only activate chlorine but they also absorb reactive nitrogen. If nitrogen oxides are present, they combine with chlorine monoxide to form a reservoir of chlorine nitrate. Dimer of chlorine monoxide, stratospheric chlorine monoxide reacts with itself forming a dimer Cl2O2. This dimer is easily dissociated by sunlight, giving rise to chlorine and oxygen atom. Free chlorine atoms will further react to destroy ozone. This is already explained. Every spring, a hole as big as the USA develops in the ozone layer over Antarctica in the South Pole. A smaller hole develops each year over the Arctic at the North Pole, and there are signs that the ozone layer is getting thinner all over the planet. Why is the ozone depletion predominant at the Antarctic? The Antarctic stratosphere is much colder. The low temperature enables the formation of polar stratospheric clouds below 20 km. Ozone absorbs sunlight, causing the characteristic increase in temperature with increase in altitude in the stratosphere. If ozone is depleted, air becomes cooler, further adding to the favorable conditions of formation of this polar stratospheric clouds and stabilization of the vortex. Vortex is a ring of rapidly circulating air that confines the ozone depletion in the Antarctic region. The longevity of this Antarctic vortex is another factor enhancing favorable conditions for the depletion of ozone. The vortex remains intact throughout the polar winter into mid-spring, whereas the vortex in the Arctic disintegrates by the time polar spring arrives. Typical happenings in the winter months leading to the ozone depletion. In June, Antarctic winter begins, the vortex develops and the temperature falls enough for the clouds to form. During July and August, these clouds denitrify and dehydrate the stratosphere through precipitation, hydrochloric acid, and chlorine nitrate react on cloud surfaces to free chlorine, and winter temperature drops to their lowest point. In September, sunlight returns to the center of the vortex as the austral spring begins and clouds disappear because of increasing temperature. This CLO and this chain catalytic cycles destroy ozone. Chlorine oxides and bromine oxide catalytic cycle destroy ozone. In November, polar vortex breaks down. Ozone rich are from the mid-latitudes replenish the Antarctic stratosphere and ozone poor air spreads over the southern hemisphere. Ozone rich from the mid-latitude replenish the Antarctic stratosphere and ozone poor air spreads all over the southern hemisphere. Arctic ozone depletion. Ozone depletion has been evident over the Arctic as well. Arctic ozone depletion, which swept across Britain in March 1906, was the greatest depletion of ozone ever seen in the northern hemisphere. The dramatic cooling of the upper atmosphere in the northern latitudes is the cause of the Arctic ozone depletion. The ozone depletion over the northern hemisphere has been increasing since the winter of 1992. Apart from the buildup of ozone depleting chemicals, the main cause is the increasing cold temperature in the Arctic stratosphere, which encourages the formulation of polar stratospheric clouds. How ozone is measured? It is done through various instruments and techniques. Some of them are the Dobson spectrophotometer and the filter ozonometer called M83 and total ozone mapping spectrometer in the Nimbus 7 satellite. The Meher technique. The most common measure of total ozone abundance is the Dobson unit, which is the thickness of ozone column in millicentimeters. Dobson is named after physicist Gordon Dobson. At standard temperature and pressure, 1 Dobson unit is equal to 2.69 into 1020 molecules per square meter. Environmental effects of ozone depletion. Decrease in ozone tend to increase penetration of solar UVB radiation. UVB radiation is most energetic component. It is in the range of 292 to 350 nanometer. It is the most energetic component of sunlight reaching the Earth's surface. It has profound effects on human health, animals, plants, microorganisms, materials, and on air quality. Effects on human and animal health include increase in the incidence of and morbidity from eye diseases, skin cancer, and infectious diseases. UV radiation can damage the cornea and lens of the eye, decreases the immune response to skin cancers, infectious agents, and other antigens can lead to unresponsiveness. In susceptible population, that is light skin colored populations, UVB radiation is the key risk factor for development of non-melanoma skin cancer. Effects on terrestrial plants. Psychological and developmental processes of plants are affected by UVB radiation. Response to UVB also varies considerably among species and also cultivars of the same species. In agriculture, this will necessitate using more UVB tolerant cultivars and breeding new ones. In forests and grasslands, this is likely to result in changes in the composition of species affecting biodiversity in ecosystem. Indirect changes caused by UVB, such as changes in plant form, biomass allocation, and various other factors like that of developmental phases, timing, metabolism, etc., may be equally or sometimes more important than the damaging effects of UVB radiation. That is, there is indirect effect on terrestrial plants. Effects on aquatic ecosystems. Exposure to UVB radiation has been shown to affect both orientation mechanism and motility in phytoplankton, resulting in reduced survival rates. UVB radiation can cause damage in the early developmental stages of fish, shrimp, crab, amphibians, and other animals. Most severe effects are decreased reproductive capacity and impaired larval development. Effects on biogeochemical cycles. Increase in solar UV radiation affect terrestrial and aquatic biogeochemical cycles, altering both sources and sinks of greenhouse and other gases. The changes would contribute to biosphere-atmosphere feedbacks that reinforce the atmospheric buildup of these gases. Effects on air quality. Reduction in ozone and increase in UVB radiation to the atmosphere penetrating to the atmosphere result in higher photodissociation rates of key trace gases that control the chemical reactivity of the troposphere. This can increase both production and destruction of ozone and related oxidants such as hydrogen peroxide H2O2, which are known to have adverse effects on human health, terrestrial plants, and outdoor materials. Changes in the atmospheric concentrations of the hydroxyl radical may change the atmospheric lifetimes of climatically important gases like methane and other Cfc substitutes. Increased tropospheric reactivity could also lead to increased production of particulates such as cloud condensation nuclei from the oxidation and subsequent nucleation of sulfur. Effects on materials. Synthetic polymers, naturally occurring biopolymers, as well as some other materials which are of commercial interest, are adversely affected by UV radiation. Application of these materials, particularly plastics, in situations which demand routine exposure to sunlight is only possible through the use of light stabilizers and or surface treatment to protect them from sunlight. Increase in solar UVB radiation accelerate the photogradation rates of these materials, limiting their life outdoors. So this ends chapter 19. Hope you all liked it. You can give your feedback in the comment section. Thank you.